Hello there. Okay, alright. So for today we will look into example 7.6. Okay. So in this example, okay, when in orbit, okay, you have a satellite attracts to the Earth, okay, with the amount of force given as 19 kilonewton, and then the satellite's gravitational potential energy, okay, is given over here. So over here they wanted to calculate the satellite's mass, okay, and then the distance from the Earth surface. Okay, value of constant g given, mass of the Earth given over here, and then the radius is given. Okay, so we derive out the given information. Okay, alright, from there, okay, we are going to determine the mass. Okay, so the radius of the Earth, okay, and then the distance from the center of the Earth to the satellite. Okay, okay, we are going to determine the distance from the surface of the Earth. Okay, unknown. Okay, and then the force is given. Alright, so by applying the gravitational potential energy, okay, it will be equivalent to g, okay, mass of the Earth, okay, multiply with the mass of the satellite over r, okay, the distance from the center of the Earth. Okay, and then if we rearrange in terms of r, okay, r will be equivalent to g, okay, mass of the Earth times with satellite over u, potential energy. Okay, we end up with equation 1. Okay, by applying equation of force, okay, gravitational constant, okay, mass of the Earth, okay, multiply with mass of satellite over r square. Okay, so if we rearrange, okay, rearrange in terms of r, okay, we will end up with root value, okay, g, mass 1, mass 2 over value of force. Okay, we have another equation, equation 2. Okay, so we can solve it simultaneously. Okay, we can equate equation 1 with 2. Okay, and then what you can do is that replacing the value, okay, simplify the equation, okay, and therefore rearrange. Okay, mass will be equivalent to, okay, u square over constant g, m, mass of Earth, times with force. Okay, so replace in the equation the values, okay, and then we will end up with the mass of the satellite. Okay, so once we have the mass of the satellite, okay, you can either use equation 1 or 2 lah. Okay, so to determine value of r, okay, so replacing the value. So once we have obtained the value of r, okay, so the r will be the distance from the center of the Earth to the satellite. Okay, now we are going to determine the height h. Okay, so minus with the radius, okay, which will end up with 9.9 times 10 to the power of 5 meter. Okay, next we look into example 7.7. Okay, so for example 7.7, the gravitational potential energy at the surface given, okay, 12.8 gigajoule, okay, where the radius is given as r. Okay, so over here they wanted to determine the work done in overcoming the gravitational force, okay, when a space probe, okay, mass given as 1000 kilogram, lifted to a height of 2r from the surface of the planet, okay, twice the value of the radius lah. Okay, so first what we do, if we plot the information, okay, so initial radius r, okay, so you have a mass located at the surface, and then what you do is that you shift it by twice the value of the radius. Okay, well, let's say we put it as r2 lah. So this is initial position r1, okay, final position as r2. Okay, so on the surface of the planet, okay, gravitational potential energy given, okay, 12.8 gigajoule, right? Okay, so the ratio, okay, multiply with the mass given of the satellite probe, okay, so we will end up with a constant value, okay, gm over r, which will be equivalent to 12.8 times 10 to the power of 6, okay, which we can apply later on lah. Okay, okay, next the final distance. Okay, so final distance, you add up with the initial radius, so where you'll end up with 3r. Okay, so the total distance will be 3r lah, from the center of the earth. Okay, so the work done will be constant, okay, g mass of earth times mass of satellite, okay, 1 over r1 minus with 1 over r2. Okay, so expand where r1 will be equivalent to r, where r2 will be equivalent to 3r, okay, which will be the final distance. Okay, so simplify it, okay, where we will end up with 2m over 3, okay, multiply with gm over r, okay, where the value for gm over r we already determined previously. Okay, so this one, okay, so just insert in the value, okay, solve the equation to obtain the value of the amount of the work done, which you will end up with 8.53 times 10 to the power of 9 joule. Okay, next example, example 7.8. Okay, so for 7.8, okay, we have a moon, okay, mass given 7.35, okay, kg, and the radius given 1740 kilometer. Okay, and then we have a probe of mass 100 kg, okay, drop from a height of 1 kilometer onto the moon surface. They wanted to calculate its change in gravitational potential energy. Okay, B, if the gravitational potential energy is lost, converted into kinetic energy, they wanted to calculate speed which the probe hits the surface. Okay, so based on the information given, okay, the mass of the probe, okay, the radius of the moon r2, okay, so this one r we convert into meter lah. Okay, so initially given in kilometer. Okay, okay, so the initial radius, okay, so this will be the initial position, and then you move it 1 kilometer away from the surface. Okay, move it 1 kilometer away, okay, which will be equivalent to 1000 meters lah. Okay, we convert into meter. So for this calculation we will use SI unit, so that means for the radius we convert lah, okay, convert into meter. Okay, so that means r1, the final position, we will end up with 1.741 lah. Okay, so over here it is dropped from a height of 1 kilometer, so that means this will be the initial r1 and this will be the final position lah, r2. Okay, so the change in the gravitational potential energy will be equivalent to the change in the energy lah. Okay, final minus with initial. Okay, expand the equation, so final over here r2, okay, initial will be r1. Okay, so once we expand and then simplify the equation, what you can do is that you can replace in the values. Okay, so where the change in energy, okay, gravitational potential energy, which will end up with 1.62 times 10 to the power of 5 joule. Okay, for question B, since all the energy, okay, energy loss converted into kinetic energy, so the change in the amount of energy will become as kinetic energy. Okay, so for calculation of kinetic energy, half mv square, so which will end up, okay, expand from there we can solve the value of the v. Okay, so which will end up with 56.9 meter per second. Okay, so for next example, example 7.9. Okay, okay, so for this one they wanted to calculate the escape speed, okay, from the earth's surface for a rocket given mass 3000 kilogram, and then B, they wanted to determine the kinetic energy of the rocket. Okay, in part A, it must have at the Earth's surface in order to move infinitely away from the Earth. Okay, so for this one, okay, first they want to calculate the escape velocity. Okay, so escape velocity, we apply the equation for escape velocity. Okay, 2gm over r. So over here the r, it is located at the Earth's surface, so that means r will be equivalent to the radius over here. Okay, so we expand. Okay, so 2gm, g constant, m will be the mass of the Earth. Okay, so just replace in the value. Okay, and then you can solve it. We will end up with the escape velocity. Okay, so once we have the escape velocity, okay, what we can do is that we can just simply insert into the equation of kinetic energy. Okay, and then expand. Okay, and then solve it to obtain the final answer. So this will be the amount of energy, okay, that will be required, okay, for it to move away from the Earth's surface. Okay, so this will be the minimum lah. Okay, so anything less than this, okay, the rocket cannot take away, okay, or take off from the Earth's surface. Okay, next example will be example 7.10. Okay, for this one, you have a rocket launch, okay, vertically from Earth's surface at an initial speed, okay, given 10 kilometer per second, neglecting the air resistance. How far above the Earth's surface will it go? Okay, so what we do is that we draw the situation over here. Okay, so take off from point A, okay, approaching point B, where point B, the final velocity will become 0. Okay, so this one, if we apply the equation of conservation of energy, so at point A, we will have both kinetic and potential energy. Okay, and then at point B, also we will have both kinetic and potential. But at point B, what happens is that the velocity becomes 0, this one over here. So that means the kinetic energy will become as 0. Okay, so by using the conservation principle, total initial energy, okay, will be equivalent to the total final energy. So initial, you will have both, okay, kinetic and potential. Final, we only end up with potential. Kinetic will become 0. Okay, because the velocity becomes 0. Okay, so if we expand, okay, so initial r1, okay, and then over here for the final, okay, so what we do is that we replace in the value. Okay, so r1 will be the value, okay, already given. So now we are going to determine the value of r2 over here, okay, which will be this value r2. So solve it. Okay, so once you solve it, r2, you will end up with 3.19. Okay, so this value r2 will be equivalent to the radius plus with the height from the surface. Okay, so in order to obtain the height from the surface, what we do is that we minus lah, okay, minus r2 with the radius of the Earth, where we will end up with the final answer over here. Okay, next example 7.11. So this one, weight of a satellite, okay, in a circular orbit around the Earth is half of its weight on the surface of the Earth. Okay, so the weight becomes half. Okay, and then mass of the satellite is given, okay, 8000 kg. They wanted to determine the altitude and then speed of the satellite. Okay, okay, so for the situation over here, what we do is that, okay, now the center, okay, radius given. Okay, so from the radius to the surface, okay, and then from the surface we are going to determine the height over here. Okay, okay, the weight at this second point over here, okay, becomes half of the initial weight. Okay, half of the initial weight. Okay, so that means if we expand, okay, it will become half of the initial weight. Okay, so therefore gm over r square is equivalent to half of the g. Okay, so expand into equation which will become half of the acceleration, okay, gravitational acceleration, okay, to determine the value of r. Okay, so once you have determined the value of r, okay, so which will be the distance from the center to the orbit. Okay, so in order to determine the height, okay, we just minus with the radius of the earth. Okay, so which you end up with the height from the surface, which is equivalent to 2.63 times 10 to the power of 6 meter. Okay, so done with this, we can apply, okay, the distance from the center, okay, into gm over r, okay, equation to find the velocity. So which will end up with 6.66 times 10 to the power of 3 meter per second. Okay, next example 7.12, okay, which will be the last example. So this one, the given the radius of the moon, okay, moon's orbit around the earth is r, and the period is given, okay, 27.3 days. Okay, mass of the earth and moon both are given respectively. They wanted to calculate the radius of the moon orbit. Okay, radius of the moon orbit. So the information given, okay, mass of earth, mass of moon, okay, and then the period given in days, okay, convert into second. So which will end up 2.36 times 10 to the power of 6 second. Okay, so simply by applying into the equation of the period, okay, and then if we expand the value, we can calculate the value of the radius lah. Okay, so which will end up with 3.84, okay, 3.84 times 10 to the power of 8 meter. Okay, okay, all right, that's all for chapter 7 example. Okay, have a nice day.